Hi everybody. This is going to be our second titration problem. Sorry, my hand is kind of cramping. I've been filming these videos all day today. It's been a long Monday, but hopefully it means I'll be pretty far ahead for the rest of the week. First thing we're going to do in this next one is we're going to remember that last time we did a strong acid, strong base, and what we assumed was that for every 1 mole of the strong acid, 1 mole of the strong base would also react, and that was a major assumption we had to make. For this one, we're going to make a similar assumption, but that for every proton that we produce, it will react with a single hydroxide ion when the reaction actually occurs. So for this first problem, the first thing we're going to do is we're going to actually write out the overall reaction, because the reaction is always a good place to start. So we're going to start with I don't know what's going on here. The acid plus, we're just going to remember that we just want the base in this particular case. Since this is a weak acid and strong base, remember that the weak acid does not completely dissociate, so we cannot make the assumption that this whole acid just becomes the proton. So when we do this, remember we're looking at the conjugate acid as well, and our favorite product, water, which gets to get ignored. Now, just like anything else, we're aiming for an ice table. Okay, so let's start with what we know. First thing we know is, again, we're going to look at V total. V total says 45 milliliters plus 50 milliliters is going to be 95 milliliters, which is going to be 0.095. We'll need that towards the end of this problem. Don't know what's going on with this pen. It's being kind of weird. And that frustrates me. Not usually a perfectionist, but you know. All right, so next thing we want to calculate is the actual moles, the number of moles of each thing that are actually present. Remember, we're using molar equivalences. We're not actually trying to do molarities in our ice tables moving forward. So we're going to do the volume times the molarity, and we're going to get 0.05 liters times 0.1 moles per liter, which is going to be 5 times 10 to the negative third moles of the acid. Then we were told we started with 45 milliliters, so we're going to do the same thing for the base. I'm going to get that value. Sorry if I'm not talking while I'm calculating, I apologize. All right, so now on the right side, we started with none of this, and we can't ignore this value like we did in our strong acid, strong base. We don't have to worry about some of this stuff, but for this, we do. All right, so now what we're going to do is we're going to realize that the change is going to be negative on the left side and positive on the right. Why? Can I subtract from 0? No, I can't. I can subtract from values that are not 0. In fact, I can subtract this number. If we're assuming that all of this is going to react because it's strong, we're going to subtract the maximum we can to get one number to equal 0 and no less. Since I'm subtracting that on this side, I know I'm also subtracting that here. And I know I'm adding that on this side. Okay, that leaves us with an equilibrium concentration of this with our conjugate base and this with our weak acid. All right, now our goal is to figure out the pH at the equivalence point. So my next question for you is going to be, how can I find the concentrations of these things? I've got CH3COOH, and I've got CH3COO. If we're saying these are present at equilibrium, both of them have a volume of that 0.095 milliliters. That's what was added together. That's the total finite volume. So our equilibrium concentrations of are going to be the number of moles at equilibrium over the number of liters. This one is going to be the 4.5. When we do that, we get 0.0053 molar and 0.0474 molar. All right, next thing to do is to plug this into the Ka expression. Now, this up here, our original equation, this is not the Ka expression. This would be something completely different. Remember that the Ka is going to be what happens when this thing is added to, or when this thing is considered added to water. So the Ka expression, and I'm going to write it over here. My Ka expression is going to come from the weak acid added to water. Review that from chapter 16. This is from 16. So Ka is going to be dependent on this expression. So this proton gets added to this base, also known as water, leaves behind the conjugate base of the weak acid and the hydronium ion. And the Ka expression from that would then be H+. Remember, please don't forget that. That's so important. I just don't want you to get confused. So then we're going to write out our expression. And we were given the Ka at the start of this problem, right? We were told certain things that give us information. So we're going to use this next with our equilibrium concentrations of these two to calculate what this one would be. So the unknown is the H+. The CH3COO- is this guy. The acid on the bottom is going to be, and we're going to set it all equal to the Ka value from up here, which is 1.8 times 10 to the negative 5th. Solve this for x, and I'm not going to show you how, but if you do it right, you should get something in the neighborhood of 2 times 10 to the negative 6th molar. You're going to take this, and since this is the concentration of the H+ ion, we're going to get pH equals the negative log of this 2 times 10 to the negative 6th. And this is a weak acid titrated with a weak base, so we're going to get a pH of 5.7. So we're not quite at the equivalence, but we're getting close is what it looks like. We're still in acid territory, and if we were past the equivalence point, this would be above 7. Remember that weak acids will have, from our lecture, weak acids will have pHs above 7 if past the equivalence. They also have equivalences of so we know we're not past equivalence because our value isn't quite above 7, okay? All right, here's your next one. This is your turn. So you're going to want to start with, for each one, the balanced equation that's occurring, and then you want to write out separately the Ka expression. So don't forget to do what I did when you're going into the second half of this problem, okay? There's your questions. Yeah. So do these and submit. If you need help, this is example 17.8. So this is like exercise 17.8. It is on page 742 of the new book, if you have that. All right, that's all.